at him from every corner of the room would undoubtedly warm his heart. After the event, you may keep the mask, whose value as a keepsake will surely decrease over the years. It actually says increase over the years, but that was my... So anyway, Chris, thanks for being my mannequin. But apparently that was done on the announcement that Peter was, being made, I guess, elevated status and standing. You had to put up this face whenever he entered the room. I expect that you can, and you can keep the announcement.
I can keep this as well.
So now, without any further ado, it's over to Marcus again, the intelligent one, to actually introduce a series of talks on past, present, future of Unix.
That's right. Thank you. Thank you, Marcus. And wow, what a great start with the panel this morning. I hope you had a good break. And this morning we look back at the origins of Unix, and while we here at Bell Labs are very proud of that history and we build on it and we recognize it and we respect and honor it, we also are not stuck in the past, but we look at the today and we look beyond today, we look into the future. So this session that we now organize as kind of a plenary talk session is intended to do exactly that. Look at Unix from today's perspective, but also looking ahead into the future. What does Unix-like systems will look like in the future? What are some of the challenges we need to address? And in order to get started, I actually want to hold up one little thing here that I want to ask, who remembers that? So for the folks who cannot see it, it's also depicted over here. Now let me ask another question. Who is still using that on a daily basis? Now, for the young folks in the audience, these are weird devices where old people put videos on and then played them back, right? So this is a VHS tape, and this clearly in the audience here, nobody's using that anymore. Let me ask a different question. Another device, this device. Who is using that on a daily basis? I saw a few hands that did not go up, really? But I think the few hands that did not go up, you probably access the web, right? And your system will be served, your page will be served by a system that is most likely rooted in Unix. These smartphones have an operating system that is most likely, with almost certainty, rooted in Unix. Now compare those two things. The VHS tape was invented or came out in the late 70s, 40 years ago. Unix, we are celebrating Unix50 50 years ago. Now, we saw, right, one technology that came out 40 years ago, still pretty young, is not being used at all anymore, while another technology, basically Unix, was invented 50 years ago, and everybody in this room is using that on a daily basis, right? And this is really amazing because the times have changed. 50 years ago, when the geniuses that many of them have in the room here started working on Unix, now, you can correct me, but I don't think you necessarily anticipated the web. Maybe the internet was just emerging, but the web? What about mobile devices? There were no mobile devices when Unix was invented. AR, VR goggles, right? Wearables, devices that go into your body. I'm not sure if the crowd that invented Unix was having that kind of vision in mind. Yet, Unix is absolutely fit at that point in time to serve this changed world. So why is that? Because of the power of abstractions and the power of simplicity, right? This is something that we probably all need to remember and to remind ourselves every single day, right? Write programs that do one thing and that do it well. Everything is a file, or mechanisms like Unix piping, we talked about that before, or fork, right? So there are some fundamental Unix mechanisms, concepts, abstractions that in for whatever reason why the folks who created Unix had a gut feeling this is how it needs to be done without knowing what the future looks like 50 years later, but they got it right. Now, we talked about something maybe wrong, but I think we generally, everybody of us using something like Unix every single day is a good attest to that. Actually, they got a lot of things right. Now, the question is, of course, will that hold up? Will we, in 50 years from now, being here, well, let's see, I will be probably retired, hopefully, but will we still be here and celebrate Unix 100, right? So that's a valid question because, again, the world keeps changing. The world keeps changing, and I want to just give two examples how the world is changing. We heard about before, right, how the Unix, Ken and Dennis and the Unix team actually developed Unix on a particular machine. the BDP7, right? And then came 11 and other machines. And, but it was always kind of running on a particular machine that kind of created a controlled environment. But as we enter the world of the Internet of Things, again, it's changing. We now have software that, again, in Unix philosophy, is being composed of hundreds, even thousands of little functions. But these functions now no longer run on well-defined machines or classes of machines. They can run on small little devices, sensors, cameras, you name it. These devices come and go, they fly, they are connected, they are disconnected, the battery dies. And will that make any change in how we need to design operating systems in the future? That's something you want to touch on. And I already mentioned the battery might die. Also, the devices we run software on these days are no longer permanently connected to a power outlet. They are driven by batteries in many cases. Does this change how we need to think about software? Do we need to think about energy when we start thinking about software? So again, the point is the environment, the world keeps changing. And I think after 50 years and Unix still being alive and kicking and dominating the world, I always say, right? I think it's still fair to take a look at some of the changes ahead. And this is exactly what we want to do in this panel here. And we have organized this panel as basically a series of 3 mini sessions, where we want to focus on kind of the 3 areas, pillars, themes, whatever you want to call them, around the kernel, which has everything to do about what is an operating system, what are some of the basic concepts and mechanisms that are in the kernel. Will they change? Do we need to rethink what we understand with an operating system? We will talk about the languages, which includes, of course, the software development languages, programming languages, software development tools. And then we'll wrap it up with a session about the compute and the algorithms. All right, and so for each of these sessions, we will have 1 or 2 external speakers, and then 1, 2, or 3 of the Bell Labs people who will talk a little bit about some of the research going on in the labs here. And to start it, I want to now invite for the session on the kernel, I want to invite Timothy Roscoe, Mothi, and Maureen Thoran on the stage, please, here. Join me on the stage, so maybe a warm welcome for them. And And I just very briefly, again, I really don't think I need to introduce the speakers here, but to Mothi, when you go to his webpage, I invite you to delete, I think it's the second line on his webpage, where he writes, "I'm a systems research person, I build stuff." But then click on the I build stuff link, and you will see a link to a paper from Rob Pike, which talks about some interesting things. And I really invite you, and I immediately liked the guy when he said I build stuff, right? So this is software research and systems is about building stuff. Now, Mothi also, he's of course at ETH Zurich, working on distributed systems, operating systems, on data centers management and complex data center systems. But it's also interesting, he's not a, what do we call that in the US, a one-trick pony. He's not that. He's not an academic and has been academic for all his life. He actually was at a startup. I think it was not necessarily the easiest time, you said, right, the startup? But he was working at the startup. He was working for a big telco carrier. He worked at academia. So he really knows what he's talking about. And it's great to have him back here at Bell Labs. And yes, I say back, because you have been here before, and you have been here for an interview for a job. And you interviewed actually with Dennis Ritchie, and I believe actually sitting on the leather sofa that you will see in the Unix Appearance Gallery in the afternoon. You can sit there and take selfies. And Mothi was there and has been grilled, and I think the interview was 1 week, you said. 1 week, not 1 day, but 1 week. In the end, he did get the job, but he decided not to take it and go on the other jobs, but we knew we'd get you back. So welcome back home. And Mothi, we will start. And then I want to introduce quickly Marina. Marina is one of our research leadership team members. She's leading the research lab on end-to-end networks and service automation. And all I want to tell you about Marina, she's just a bundle of energy. All right, that's all you need to know. She's the czar of network slicing, of software-defined networking. And I dare you, maybe in one of the breaks, take a cup of coffee, take a couple of snacks, walk up to Marina and whisper the word slicing in her ear, and she will get going. Your head will explode with ideas later on, so Marina will follow it. And with that, Mothi, why don't you come up and get us going?
Okay. Thank you, Marcus. That was quite a build-up. As I feel extremely honored to be here and slightly humbled, and I feel I also have a difficult act to follow, given what we just saw before the break. As Marcus said, I actually was here 25 years ago, pretty much 25 years ago next month, I think. I am roughly as old as Unix. I don't know whether that's a good thing or a bad thing, and so it feels a little bit strange, a little bit nervous to be here speaking in front of such, sort of figures who are so involved in the very origins of this kind of thing. 25 years ago, I was pretty nervous as well, and one of my abiding memories of my interview here, which turned out to be actually very enjoyable after I got over my initial fear. One of the things that actually put me very much at ease was that I was ushered into the office of Dennis Ritchie, and I was, of course, I was terrified. This was Dennis Ritchie, and Dennis was very, very nice to me and very warm and very friendly and made me feel a lot better about it. With that, I will try to say something intelligent about Unix, which is what they asked me to do, in front of a bunch of people who know far more about the system than kind of I do. But I spent a lot of time working on operating systems and things like that. Unix is, in a sense, the iconic operating system. Almost any operating system in the world today, if you talk about it, you either talk about the fact that it's derived from Unix, or you talk about the fact that it is different from Unix in the following kinds of ways. Unix is, in a sense, the reference point for almost any operating system design, even if it doesn't actually look like Unix. And so one reason I feel nervous is I spent most of my career trying to build operating systems that are not Unix, which is probably a little bit different to many people. But many people who actually build operating systems today just assume that an operating system looks like Unix. It has that kind of status, that kind of influence, that kind of impact. And of course, when I build operating systems, what do I use as a development environment? I use Unix, right? My laptop runs Unix, my phone runs Unix, because I honestly, since discovering this at university many, many, many years ago, I haven't actually found anything that works better or that I like better to use. So my life has been a constant frustration in that sense. But trying to write operating systems that don't look like Unix really gives you an idea of some aspects of Unix, the unexpected aspects of Unix in some sense, that are incredibly important to the way the system is built. And so, trying to come up with something intelligent to say to all these people who know more about Unix than me, I thought I'd talk about fork, right? Because fork is a particularly interesting little part of Unix. I say little, but I will try and sort of hopefully modify that during the course of this talk. So what about fork? Fork probably doesn't need much explanation to people in this audience here. Fork is very simple. Fork is how you create a process on Unix. You call fork returns twice, once in the process that called it, and the other in the new process that's been sort of been called. Fork is beautifully simple, right? It's a very, very simple primitive. It takes no arguments. It returns one integer. It doesn't get much simpler than that. In the early sort of documents about Unix and the original papers on Unix, it's described as being derived from a system called Project Genie, which had another system called fork, which created a process. That's actually true, but if you go off and actually read the documentation for Project Genie, you'll notice that actually it's a little bit different, right? The actual manual, and myself and actually Andrew Bauman, my colleague who's now at Microsoft, went off and looked at this. The manual for the Genie fork is actually much more complicated. It takes a whole load of arguments that just determine how you actually create a process. And so when fork went into Unix at a very early stage, it wasn't like this. Fork, when fork was put in, I think in the 3rd edition, but I'm not going to prefer to be corrected on this. Fork was much simpler than this. It was a radical simplification. In that sense, it embodied a lot of the nice things about Unix, was that it radically simplified things. It radically simplified the abstraction for files, as we heard earlier this morning, for instance. So fork in Unix only does one thing, and it does a complete copy of the processor's address space, and in principle, almost all the sort of the kernel state. So why does it do this? Okay, I don't know why it does this, and unfortunately, Ken isn't here. Dennis is no longer with us, unfortunately, and I wish I'd asked him when I was here 25 years ago. but I hadn't really thought hard enough about it at that point. But in the evolution paper that Dennis wrote, he actually says, that this was basically there because it was really simple. It was a very elegant hack. It was 27 lines of assembly in order to create a brand new process. That's actually, that's the kind of thing that people like me find really, really cool and really nice. It's a very sort of elegant way of doing it. And particularly on that machine, with that kind of memory, that kind of hardware, it was beautifully simple, elegant way of doing it. It was a really nice thing to do. It was part of this great sort of radical simplification that I think is one of the terrific lasting contributions of Unix. Okay. And so in that sense, it's great. It also separates the notion of creating a process from the notion of what you actually want to run, what you actually want the process to do. It allows you to do anything you like to configure the process in your own code, rather than going to the operating system and saying, here is a massive load of arguments, here's what my process should look like. No, you just create the process. It's just the same as the process you had before, and then you run your own code in that process to make it look the way you want it to. Ultimately, probably running exec or something like that. So in that sense, it's got a very nice, clean orthogonality about it. Okay. And so in that sense, fork is quite nice. Unfortunately, I think for me, someone who's trying to do something different, fork has a very interesting effect over time, right? And if you look at what happens with fork now, on machines that are very different from the machines that Ken and Dennis and the rest of the many people here were working on in those days, fork now has a very interesting effect on the design of an operating system. If you decide to write a new operating system today for a modern computer, you face a very clear choice. Do you care about fork? Do you care about fork working well enough to build a kind of reasonably usable system? Right? And I would claim that there are two options here. Either you do, in which case, if your operating system is any good at all, it's going to look like Unix. It's probably not going to be as good as Unix, but it's going to look a lot like Unix. If you're really smart, it might actually be an improvement on Unix, but because this has been done. I'm particularly fond of Plan 9, for instance, which of course was written by the same people, but is a nice kind of evolution of that kind of thing. But you're going to write something that looks like Unix, or you're going to write a bad operating system. And there's probably a sort of Venn diagram there. If you decide not to write Unix, you have to sort of say, well, okay, I'm going to have to just get rid of fork. I'm going to have to do something different. That's a very interesting choice, and I've come to this conclusion rather reluctantly over many years of sort of thinking, oh my goodness me, yes, this is really at the heart of Unix. And so in a sense, fork is Unix. Fork defines Unix in a way that it didn't, I think, when it went in. Right? We talked about the file system being one of the really key, elegant features of Unix, and Unix was organized around the file system. And the early papers talk about this, which I think is absolutely true. But if you look at a modern Unix system, it's not actually organized around the file system anymore. It's actually organized around fork. Okay? And I think that has some very interesting consequences for the future. Okay? I think it was partly a success sort of factor, but it's also something that looks at it, we need to worry about for the future. Because fork is not what it was. And so if I actually go back to the original simplification that we had with fork, it's very beautifully simple. It just creates a complete copy of the process. If we look at what happens now, here is the POSIX specification of fork. And it says, it's this beautifully simple thing. Fork function shall create a new process. The new process shall be an exact copy of the calling process. Wonderful, except as detailed below. So this is a fairly brief description, but it turns out that, in fact, there are quite a lot of things that fork no longer does. Well, no, fork does what it always did. But there's a lot of things now that you might expect fork to do that it doesn't do. For instance, you might have a multi-threaded program. This was simply not an issue when Unix was around, right? Unix, in a sense, created new processes, that wasn't really a multi-threaded programming system. It is now, of course, and that's fine, and it handles threads reasonably well. But if you've got a multi-threaded program with lots of threads running and you call fork, you get one thread in the child, and that happens to be a copy of the thread that happened to call fork. If you've got a bunch of other threads that just happen to be holding a lock, say, sorry, you've just created a rather difficult situation in your child process. There are many examples of this, right? And this is despite the fact that fork itself, for large machines trying to do this sort of copy of the complete process, is an enormously optimized system. So much of the rest of a modern Unix-like kernel, right, for good reasons or bad reasons, or maybe a combination of the two, is about making fork go fast. And unfortunately, I think we're reaching the point where this is actually becoming something of a problem. And the actual performance of fork itself, when I have a large program, despite all the cleverness with copy on write and lazy update of page tables, all sorts of very, very smart stuff, lots and lots and lots of complicated code in a modern, say, Linux kernel or a BSD kernel or something like that, is about making fork go fast. And yet it's still surprisingly slow when you have a process that's doing a lot of busy stuff. Okay. Compared with just trying to combine the two, fork and exec, into something which is a lot less flexible and is a lot less elegant and bundles up a lot of functionality that really shouldn't be tied together, and yet appears to go incredibly fast on the system, like about half a millisecond compared with many milliseconds for forking and execing a complicated process. And I find this sad because I like the elegance of fork, okay? But I don't like the way that it's become, if you like, an albatross around the neck of the kernel. And so I think there are sort of reasons for this. How did fork become so complex? There's a lot of things that have been put into Unix that were just simply not there at the start. There are GPU contexts, threads, virtual machine support, a lot of stuff with asynchronous I/O, per process time, all sorts of facilities, which were not in the original version of Unix. If they had tried to put them in, you'd have ended up with something like Multics or worse, right? The whole point was to get rid of a lot of this stuff. Now that it's back there, then we do have this interesting issue, which is this stuff is difficult to support with fork, and a lot of effort goes into partially supporting it, or documenting the fact that it's not supported with fork. We have very, very large memories today, right? I have friends who build machines with terabytes of RAM, okay, and very big cooling fans. And a process is not what it was. The beautiful thing about Unix was a program was a process. You want to run a program, you create a process. If you want to build a pipeline, you compose a bunch of processes. Unfortunately, this is not the way that people use computers today. Right? Ironically, in terms of sort of single-user operating systems, right? The operating system that's close enough to that model, the model where an application is a process, right, is actually a different operating system written by a large company on the other side of this country. Right, which actually retains some of that model, except they're massively great big programs. But on Unix, no, we use processes for all kinds of things. A web server just forks a load of worker processes all over the place. Okay. So the workload is different. The way the operating system is things the operating system is expected to do is different. From my point of view, the other thing that's very interesting is that the hardware is very different. One of the things I love about Unix is you look at the hardware and you think, this is just the right thing to do on hardware like that. Okay. So for instance, here are the lies that we tell our children today. I speak as a university professor who teaches a course based on this fine textbook from Randall Brown and David Halloran at Carnegie Mellon. It's a great textbook, but it has this wonderful picture here. Right? This is the third edition of this textbook, 2011. They've got a new one coming out, but this is the diagram, and it says, don't worry about the complexity of this figure just now. I actually do worry about the complexity of this figure. I actually worry about the lack of complexity in this figure. This is a fantastic machine for running Unix. If you ignore the details in the words, this could almost be a picture of something like a PDP-11, certainly. I actually was fortunate enough as a student, somebody gave me a PDP-11. She gave me a PDP-1134. It was huge. I don't know why I got rid of it, but this is that kind of machine. This is the kind of machine that makes Unix so great, the way Unix really makes sense. Unfortunately, if we look at the phones that are in our pocket, simply the main SoC on that phone actually looks rather more complicated. It looks like this. And this is not the machine that Ken and Dennis wrote an operating system for. Every circle on here is a different processor. Right? They do different things. They share memory, but only partially, and maybe or maybe not cache coherently. Certainly not, they don't share virtual address spaces. Okay? The idea of a process on this machine is really quite problematic. The idea that Unix and the beautifully simple model of Unix actually works on this machine doesn't really play out. The reason that you can actually run a Unix-like operating system on a phone is that it's only really running on those two dots in the corner there. And this is a 10-year-old chip. They've got more complicated since then. Okay. Now, to me, as an operating system person, this is kind of frustrating. I like writing operating systems, even if, trying to write operating systems that aren't Unix ends up, can sometimes be a slightly sort of futile business. But writing an operating system for this is an enormously complicated thing. And of course, other phone SoCs are different. There's a new one of these being produced every couple of weeks or something like that. Right? And they're all different. So what can we do? Right? I think this is the sort of the bit where I sort of look forward to the future and say, I think that the Unix model, the way that the actual details of how Unix does things, and a particular fork, which has come to dominate so much about how Unix works, apart from, to dominate all the other beautifully elegant ideas in Unix at the time, is running up against these kind of things that the hardware people are throwing at us. And I think we need to do something different. And I think, the way I would sort of, try to end this talk, and hopefully I haven't sort of annoyed too many people so far or offended too many people about this, is I think we need to think about, what is the sort of moral equivalent of Unix, but in this kind of hardware landscape. If I wanted to do this again, or if somebody else wanted to do this again, how would you apply that kind of Unix philosophy to this kind of hardware landscape? Right? And I wish, in a sense, that I was smart enough to be able to do what Ken and Dennis did when they looked at the complexity of Multics and the complexity of that hardware and then said, we could do something much, much simpler here that would actually do pretty much everything we wanted and yet have so much more potential to the point where it's still, in a sense, the dominant model for operating systems 50 years on. And so I don't want to get locked into a particular orthodoxy about the right way to do things in the same way that, being locked into the orthodoxy that, well, your disk had to have structured record files on it was orthodoxy 50 years ago. I think, the Unix kind of thing here, Unix philosophy should really be to sort of look at this modern hardware and say, look, hang on, what can we do that actually introduces some notion of simplicity and elegance in this? I often look at manuals for these kinds of chips that I showed there, which are about 6,000 pages of PDF, by the way. Right? They're really quite daunting. But I can't help sort of thinking, sometimes it's kind of, if Ken Thompson and Dennis Ritchie were staring at this manual today, what would they do? And I think that's a really interesting question to ask. And I wish I was smart enough to know the answer. I think I can, come up with some ideas. This is clearly more of a distributed system, right? This complicated thing. Is this working going back here? This thing here looks a lot more like a distributed system. So maybe you have something with very simple kernels and then some sort of distributed systems thing. But we were talking about this morning in the tent outside. I think that the thing that we're really lacking in so many different areas is, what is the equivalent of Unix for distributed systems? Unix became this reference point. It became this beautifully simple model. And it sort of, in a sense, grounded everything else. We have never done that with distributed systems. There has never been the distributed system model, the piece of kind of middleware, the way of doing distributed objects that actually captured the essence of what you really wanted to do in such a nice way that Unix has. If we come up with that, then maybe that's actually the basis for the operating system kernel, or collection of kernels, if you like, that we might want in the future with this kind of modern hardware. But I don't know. But I'm really curious as to what the people who, smarter than me, who came up with Unix would have done when faced with this landscape. I'll stop there. But thank you very much for listening, and I hope, I feel very honored to be here.
Well, Thank you very much, Marina. We will take Q&A later on as basically at a wrap up for the mini session. And Marina, why don't you take it from here?
Thanks, Marcus. So that was a good introduction. Distributed systems. What is the right OS for a distributed system? And networks are distributed systems. So one of the things that I want to share with you today is how we're going to look at the paradigm shift that was caused in the management of networks and managing the complexity of networks, and how we're using Unix as a way to be able to inspire the way we would approach the managing of this distributed network. So let's look at what made Unix success. It's really its simplicity, like Timothy pointed out. And what were the reasons for its simplicity? It's a couple of basic concepts that it was looking for. It was user-centric with the help of supporting time sharing. It was programmable and portable through the help of system limit primitives, as well as abstractions. And then it was also able to compose itself using files and pipes and these very clean notions of how you actually build these programmable systems. But can this philosophy be able to use to inspire and manage network complexity? So what is network complexity? There are two main points. There are lots of things that all of us working in networking know about are real challenges with networks, but I just want to point out the two main things that we've been dealing with. One is the ability of networks to be able to support an increasingly demanding set of network services. So I'm showing you a picture of bandwidth and latency, and you can look at all kinds of applications that we are having to support today on networks that have varying requirements of bandwidth and latency. And this is very different from what it used to be a few years ago. In addition to that, these networks need to be optimized on the fly to meet the services. So in an on-demand cloud scale world that we live in, we want to be able to deploy and manage these services in real time. And these service requirements are not just one and done, or it's not set in the beginning and it's fixed for all time, because sometimes these services might require more bandwidth, require more latency constraints, or additional requirements that come in because you're going to be able to maintain the entire life cycle of the service. So this is one of the challenges that you're going to see with supporting network services on the network. And another complexity component of networks is its scale. So this is just a snapshot of a very small network that you will see later today in the lab. This network is actually a full end-to-end Nokia network. It covers multiple different network technologies. And we're supporting services end-to-end on this network infrastructure. Now, this is just a very small-scale network. In an operator environment, this is orders of magnitude more than this complexity that you would see in terms of scale. Now, to top it all, we also have the challenge of dealing with multiple vendors because no operator runs on a single vendor network. So you're going to have to deal with multiple vendors that are also there within the network. So with these two types of complexity, how can we use some of the simplicity and the concepts that was used in Unix to be able to inspire the development of something that will, an operating system to manage the end-to-end network? So let me go over what we do today in networks. So today's multi-vendor, multi-domain networks that are handled are usually managed as silos. They usually have single vendor domains that are managed with a network management system, and then you have the problem of having to coordinate the resources across these different vendors, across these different domains of the network, so that you can provision services. So the operational complexity of these systems are really large. So it would be interesting to see, like, when you have such a system, and Peter mentioned earlier that networks have always escaped from the control of computing platforms and computer science experts. But this is a perfect opportunity for us to actually start to apply computing principles to being able to manage the operational complexity of the networks. And there are two reasons why I believe this is the right time, because one, we're starting to define networks using SDN, or software-defined networks. We are also trying to minimize the amount of hardware to just the basic needs that need to be optimized on the hardware, and virtualizing a lot of the network functions so that they really become more programmable and software entities. So this is a good time. So if you want to come back and bring back all your innovations in the space of designing new operating systems, it is a good time to come back to Bell Labs and start doing this work. So what we want to do from taking an inspiration from Unix is to actually say that, well, we have these multi-vendor networks, and we want to be able to manage these network resources, much like what Unix was trying to do, is to be able to manage and schedule these network resources. So we want to decouple the hardware from what needs to be done for end-to-end service automation. And the way we do this is with domain management systems. And the special thing about these domain management systems going differently from what was used in the vendor-based network management systems is to start building it using models. So what kind of models best describe these networks so that you can actually provide the right level of abstraction, so to speak, to the higher layers so that you can actually build an operating system to achieve that end-to-end network programmability. Now, it's not a simple system. You have hundreds of knobs, many different details, and the devices have their analog resources that you need to manage and control. So there's a lot of complexity in how these models need to be developed. And also, there's not much in terms of standardization. So typically what standards do is just give you a description of all the configuration details of how a particular network element needs to be configured. But it doesn't tell you to view the network element as an entity that is providing a service or it's supporting how you provision services on top of that network element. So that's actually where we are trying to change the way we think about network management. Rather than managing a device or a network element, to start to think about how do these elements come together to be able to provision a service on top of it. So you reduce the complexity of what the model has to actually support to be able to provision services. So we started to look at abstractions. And so some of you may remember, we used to have a project called NetML. I don't know if any of you were here at that time, but this, I think Steve Fortune, I saw him in the audience earlier. So Steve had actually started working on something called a net inventory tool. It was a way to be able to discover the network and be able to capture that in a way that actually allows you to be able to express the different combinations of how these different elements of the network can be put together. So it has some basic set of primitives. You can use a couple of primitives such as a link and an adapter. And using the link and the adapter, you can start to almost build up the entire complexity of the network through adaptations and through multiplexing, through disaggregate to demultiplexing. You can build out the entire model. So when you think of a service, and a lot of the algorithms that we use to be able to provision networks use these basic assumptions that how you build a link, how you build a connection, and how do you create the aggregations. So this is what the network algorithms always do. So using those concepts that are used to plan and manage networks, we built these basic primitives. And these primitives form the basic abstractions that we want to use to be able to model the different network domains that need to be expressed up to the higher layers. So what are the expectations that we have of these abstractions? So if the abstractions just remain as mathematical terms, they're not very useful. Mathematics is important in order to be able to trace how the services are provisioned through the network, but they should also be able to convert into something that is configurable. So you should be able to send down configurations down into the network domains. The other part of it is, once you have provisioned the network, you want to be able to say what we're doing in terms of verifying that the service level agreements have been met for that particular service provision. So we have built a novel capability to model the cross-layer multi-domain network. And one of the challenges that we're dealing with here is with the distributed OS, you have these network elements are distributed. How do you maintain the consistent state of that network? The other concept is using network intents, and in this case, what we do is we use declarative intents that allow us to be able to specify what networks are supposed to do and not how they exactly do it. Now, these intents, so to speak, needs to be forked onto the distributed elements of this entire network. But once the intents come to the network operating system, you want to be able to compile the set of intents and be able to put it into these domain management systems to be able to configure the domains. And these things are continuously being monitored so that you can go back up and make the automation of the entire life cycle of the service. So we put these two concepts together and built our first prototype called Net Unix. It's a little bit ambitious goal, and I think Timothy was talking to me about this morning. Do we have the Unix for the network now? And we want to build this network operating system in such a way that the network operator has a perspective of having an illusion of infinite network capacity by providing the right level of abstractions to be able to provision services. And this is being implemented across this end-to-end network, along with the software components, which we called as virtual network functions. So what we also want to do is that, will this network OS allow us to be able to do network sharing? And Marcus mentioned slicing. So slicing is an interesting concept where we're actually trying to create dedicated resources inside this network and with the software and the hardware components to be able to guarantee a service that needs to be provisioned on this network. So we have slice managers that receive the slice request, and then the domain managers are orchestrating these resources to be able to provide the slice, and it's continuously monitored to be able to provide the right level of quality of service for that slice. So as you can see, we have different types of services that are low latency, high bandwidth services that are done. Now, all of these things, we pulled it together to be able to show you an end-to-end network, which is what we will show you later in the lab, and slice is being orchestrated with the first step of building a network operating system. So this is an operating system that is actually orchestrating the end-to-end network to be able to provision. The lines that you're seeing here, the pink, the connections to the sleeve and the robot, those are all the slices that are being provisioned on top of this end-to-end infrastructure. So is this the end? No, this is really the very beginning, because just like Moti mentioned, there's a need for an operating system that manages distributed systems, but we also want to be able to scale these, and we want to be able to actually program this network OS. And this is being done in the context of having 100 times more, I'm looking at the time, there's 100 times more capacity that needs to be met for all these virtual reality, augmented reality types of applications. But also we want to create the latency to be as low as 1 millisecond, or less than 1 millisecond, right? So that also poses interesting challenges. And we want to continue to provide carrier-grade reliability, because these services have to meet 5 nines or better in terms of making sure these services are instantiated. So it's a great time to actually go back to looking at operating systems. It's a great time to bring computing and networking together, and I think the time is right to define this new network operating systems, and we call it NetUnix. Thanks.
Thank you, Marina. And I actually want to take a few minutes to build on what Marina just talked about, right? She talked about how we create this connectivity now between all these distributed resources, and this allows us to now actually develop software and run software on this globally distributed systems, or as we call them these days, clouds. All right, but one important aspect that we also need to keep in mind is these clouds that we know and use today, they might have originated from a relatively small number of very large data centers, but they are distributing out into the network and on-premise, and for good reasons. Latency is one, latency-sensitive applications, high bandwidth applications, taking advantage of all the processing power that we have available globally. So one aspect that we really need to keep in mind is that the clouds are actually no longer deployed in a small number of large data centers, but they are moving out. And the numbers that you see here are actually from one of the national big carriers, so to give you a little bit of sense. So just a few cloud centralized data centers, but then in the hundreds, basically, we have the metro edge clouds, and then it goes all the way to the several 100,000 in the cell tower sites or the enterprise sites in the millions. If we thought that managing a cloud today, managing a data center was a nightmare, then I think we are in for a nasty surprise, because managing this, all these resources that are now distributed all over the network, this is really a big task. And why is that such a nightmare today? Because today we rely heavily on what we call manually scripted control. We rely heavily on human experts that understand the application needs, take a look at the cloud resources, then try to imagine every possible state the cloud could take, and then try to decide what action the cloud should take. This is what we basically specify in configuration scripts or OpenStack recipes. This is where all the work goes in. So if you think about it, we have not really solved the problem of managing these clouds. We have just shifted it to specifying what the cloud should do. Once you did that, you hand it over and the cloud can magically scale, but you still have the human in the loop today. And I can tell you that from first experience, because my team, our teams, they are deploying things on the clouds. And I can tell you how often I had the team leaders and department heads standing in my office saying, Marcus, I need more people, I need more people, I need more people. I asked why. They said, we need to do so much work configuring these things and running these things, deploying, making sure they run. Well, then I said, well, the right solution is not asking for more people. The right solution is augmenting the people, and actually automating that process. So the team got going and actually started at using initially statistical methods, but now increasingly machine learning also to really automate this whole kind of configuration and management of clouds. And what we started doing together with some of our partners is actually building what we call a cognitive cloud control system that takes the burden of having to specify how the cloud should react in certain situations away from the human and does it by learning, by self-learning, by actually looking, observing the workload patterns, observing the reaction to certain things, and over time then actually learning what the different behaviors are. If you think about it, this is not that different from a self-driving car, right? A self-driving car maybe learns not to crash into that yellow, Toyota, not to crash into this purple minivan. It never saw a UPS truck, never saw a tractor, but it knows not to crash in those two things either. It learned that using machine learning techniques, and that's exactly what we do in our cloud. We never see all the potential states the cloud can go into. We don't need to. We see a few states, we see how the applications react, and then we use statistical methods and machine learning to infer the millions and millions of other states and to understand what we need to do. Now, this is in particular interesting because I mentioned before the clouds distribute out, right? They go from the centralized data centers to the metro, to the far edge, on-premise, but this is not where the clouds will stop. The clouds will even go further beyond on-premise and start going, and they do that already today, going into our devices, into our sensors, into our watches, into our phones. These are also cloud resources that we increasingly start tapping into and load software components onto those devices as well. And there are good reasons for this. These are driven by real applications. Right? We all know from the consumer fitness space or the medical health area space, variables, sensors, heartbeat, step counts, and so on. But more interesting are, for example, the industrial use cases where we want to basically provide the workforce in the field additional intelligence, additional knowledge, as well as, for example, using augmented reality techniques where you have these goggles or other devices that need to execute software on the devices themselves. So there are good reasons why we actually see this happening. And the question then is, how do we build software for a world in which we actually have to run certain components on the devices themselves? In particular, if we also need to run machine learning models on these devices themselves. It's not just the traditional kind of software programs that we coded together, but we also need increasingly run machine learning models. And this is tricky to do in an environment where you have all these little devices swirling around, they come and go, and you might even, at some point in time, see a device that you never saw before that you want to take advantage of. And so my team did a couple of experiments and actually to look a little bit into what some of the implications are for software. And I want to pick just one example that I think illustrates that this is a quite interesting challenge. And the example is a very simple one. We actually took a machine learning model that its purpose is to detect a wake word, like, I don't know, hey Siri, Alexa, or your favorite name, and actually trained that model to detect a certain wake word, and we trained that on an iPhone 7 model. And it's very easy. There's no magic behind that. We quickly achieved an accuracy of about 80%, and then we took that model and actually deployed that on a Samsung S8. A slightly different phone, a slightly different device. And what we observed that the accuracy of that wake word detection dropped by 35%. We then looked a little bit into why that is. And there are little differences maybe in the hardware, but even if the hardware is identical, the software pipelining, the software processing on the hardware makes a difference. And we noticed that there are differences in the spectrograms coming back, and that completely threw off the machine learning model. When I say completely threw off, we saw a drop from 35% in accuracy. Just to put that into perspective, for wake word detection or for automatic speech recognition, over the last 5 years, the improvements you achieved were 10%. So if we drop by 10% in accuracy, we nullify the research work of 5 years. This is dramatic. So this is not something we can ignore. On the other side, we cannot train the machine learning models for every device that might potentially come and cross our field, right? This does not scale. So how do we write software, just like what Unix was written 50 years ago? How do we write software in the world that I just described so that the software still runs valid, powerful, and accurately 50 years from now? Another example that I hinted to before, a lot of these devices, many, if not most of these devices, are no longer plugged into an outlet. They run on battery. And while in the past we could ignore kind of the algorithm complexity roughly doubles every 8 to 9 months, we could ignore it thanks to what? Thanks to the Moore's law, right? So Moore's law roughly kept up with us. And yeah, I know there are discussions whether Moore's law continues along that path, so that's one challenge that we have. But let's assume for a second that Moore's law will even keep up, will give us this continued improvement in processing power. Now keep in mind what I just said, that these devices, many of these devices will run on battery. That's another problem we need to start thinking about. Because the improvements and the progress in battery technology, for me, have been very disappointing. It doubles only, battery energy density doubles only every 10 years roughly. That's not even close to what we need. So do we need to start thinking about maybe designing energy-efficient software? Do we need to take that into account as well? Well, even if you're an optimist and say, well, battery technology will go with us, well, some bad news here, right? All the lithium in the world will be, if we continue on that path, will be taken up, absorbed, gone by 2050. These are several studies. So a clear sign that something that probably was not necessarily at the forefront when Unix was started 50 years ago, suddenly becomes much more relevant and interesting for us. So we started together with several groups at Bell Labs, also together with some of our external partners, to pull several of these pieces together into something that we call Sensix, which is basically a platform, a software fabric that allows us to run software, in particular also machine learning models, on all these embedded devices in very efficient ways. We have ways to optimize the runtime, to reduce the energy consumption, to reduce the storage and memory footprint, for example. We have ways to take care of what I mentioned before this, when a new device comes on, using transfer learning techniques. And we are starting to build this software fabric that actually will allow us to run all these software modules in a very robust, stable way, also with the accuracy need, and hopefully in a future-proof way, so that hopefully in 50 years from now we can say there's a piece of software that we wrote today that is still valid then. Okay, with that, let me wrap up here and for this mini session. Thank again Marina and Moti, and start the Q&A session. Now, I don't know, we have the microphones in the room, I guess. And we have maybe time for 2 or 3 questions. Any questions? Doug.
I would like to ask if for this grand distributed operating system, you could write a paper as concise as Ken and Dennis's original paper, as revealing, and if not, why not?
So your mics are still on?
Is it on? Okay. I've asked that question myself. I think there are a few reasons. One reason is a specific thing about the academic publishing culture, I think, which is now that papers have to be, the requisite graphs and equations have to be in and everything else like that. And it's actually very hard now to write operating systems papers, because typically the kinds of things that you really care about in an operating system are the kinds of things that the Unix time-sharing system paper actually talks about. That would never get through the program committee these days. And I think that's, I happen to think that's terribly, terribly sad. Because some of the most influential papers, certainly the papers I've read that have been most inspiring and made me think in different ways, have been that kind of paper. Could you do this for a distributed operating system? I think if you could, then you've got the right operating system, right? I think, in a sense, the goal, perhaps, you'd flip it around and say, our goal should be to try to produce some way of coordinating a distributed set of computing resources that can be summed up as succinctly as the original Unix time-sharing paper did for essentially a single kernel and a set of utilities and things on top of it. The one caveat I give is I do think the problem is a lot more complex. And I think there's two reasons for that. One of which is the hardware is more complex, and it's not clear that it needs to be. The other is that I think the problem, distributed systems are just complicated anyway. But it's something to aspire to, certainly, yes.
All right, thanks, buddy. Margo, over here. Barbie.
Okay, I'm sorry, Mothi. I feel like I should channel Jochen Leidke here. And his claim would be that, you know, the microkernel architecture is exactly what you're describing, right? Which is that the way you build a distributed system is fundamentally, it's all about messages and IPC, and that we've known how to do that for 20 years, and the rest of us, and I include myself with you in this, are just stubborn and didn't pick it up. So I'm channeling Jochen.
Yeah, absolutely, and you know, Joachim is another person. It's very sad is no longer with us. But the microkernel is not the solution to the distributed systems complexity problem. I happen to think that, you know, something like a microkernel is probably the right thing to do now for the kernel, but the problem is elsewhere. And Joachim wrote some great papers, and some of Joachim's papers are fantastic. Again, they've been hugely influential on me. The worst paper by Jochen Leidke I have ever written is the one where he describes how to build a complex, complete system on top of a microkernel, and it's called Clans and Chiefs, and it's a disaster. And I think that's because microkernels do sort of solve a particular kind of problem, but that's not the problem of building the simple distributed operating system that Doug was talking about. I think that problem remains unsolved.
Okay, we have time for one more question. We already have a microphone over there.
So I want to take a stab at Doug's question, and I want to say that I think that the complexity, software, hardware, everything is, you know, as the cliche goes, is like a gas to expand to fill the universe, and it goes until whatever the container is. And the problem is we don't have a container like Doug around, and without a container, complexity, entropy rules. Yeah. And so one container used to be Moore's Law, and what I'm hearing right now is there are a ton of startup companies, even big companies, building GPU-like chips, and they're all different, and they're all out there. And the reason seems to be because it used to be that Moore's Law would force everyone to build the same thing. They couldn't afford to have anything that wasn't general purpose. Now you can afford to do specialty items, and so the design you have has got a specialty item of everything in there. And there's going to be more and more. That you showed the design from the last phone, but what about next phone? It's going to be worse, right? Yeah. Not right? Second verse, same as right. Yeah. Anyway, so I think the real problem is we don't have someone around like Doug who tells us that in fact there is a container, and we just don't realize it. If we had a simple solution, it would win. But right now, the program committees, the authors, nobody wants the simple solution. They all think more is more.
Okay, so with that, we need to wrap up for this session. I want to thank you again, Mothi and Marina. Thank you very much. And Mothi, why don't you stay up here? Marcus will present you also a little something there.
Yeah, Mothi.